few more lectures, and I thought I would talk about more fun stuff rather than continuing to proceed methodically. So last time we started with I'm not going to give precise names for the flavors of categories we're talking about, but we had some kind of braided category. Secretly, of course, a three category. And it may, but we, for much of what we said, we didn't need to assume this modular assumption, which is that the determinant of this matrix is not 0. And so from this, using the usual machinery, we get a 3 plus 1 dimensional TQFT. And if we were in the modular case, so this 3 plus 1 dimensional TQFT, probably it's not exactly the same, but probably could reasonably be called a Crane-Getter Kaufman type theory that the state sum that we derive is similar to theirs. Or the one specialization of the state sum is similar to theirs. But in the modular case,
so what exactly are the adjectives you need to get the state sum?
Well, pre-modular is one term that's used, and I think braided fusion category is.
Oh.
I think, but what you need, again, I don't know.
Yeah. I'm
not good at remembering them. I think there's too many category names, so I sort of, as a protest, refuse to remember any of them except basic ones like braided. What you want, finitely many objects. You want things to be, the three-dimensional version of pivotal, so you can turn them around, and that's about it. You want some non-degenerate inner product spaces, maybe positive, and that's enough to. So what you want is whatever assumptions on this one category allows this corresponding string diagrams to be unambiguous pictures in the three ball.
So it's really the case that the finiteness condition that gets you from a 3 plus epsilon TQFT to a 3 plus 1 totally ignore the braiding. That's solely a condition that you can talk about on the underlying tensor category.
Yeah,
forgetting the
so. Yeah.
Okay. It seems a little strange. I mean, is that peculiar? Is that an accident or?
No, I don't. I mean, one thing you need to check to go from 3 plus epsilon to 3 plus 1 is that the scheme modules are finite dimensional.
The scheme modules for all the different three manifolds.
Yeah, three manifolds. Yeah. And because these are ribbon pictures, we really just need to check, sort of the one skeleton of the three manifold.
Oh, I see. So really the fact that there's one trivial level here is what lets us.
Yeah. I think that you'd have to say something more complicated if you had some kind of general thing.
I see. So more generally, when you have some n category with a bunch of boring levels, with k boring levels, you can think of that as an n minus k category with some extra structure, like braidings and tensors and so on. And the statement is always going to be that to get from an n plus epsilon to n plus 1 category, TQFT, so an n plus epsilon to an n plus 1 dimensional TQFT, the extra conditions you need are statable solely in terms of the n minus k category, without referring to the extra structure coming from the k boring levels? Or is that too much to hope?
I'd have to think, I haven't thought about it, I think something roughly similar to that is probably true.
Okay.
Because we want, I mean, the other assumption I threw in there, which is kind of a bigger one, is this sort of positive definite product, which sort of would allow allows you to bootstrap statements like the one we just made to higher dimensions. In any case, so, you know, from this particular sort of 3 category, we, as expected, construct a 3 plus 1 dimensional TQFT, which is what we've been doing for the last several lectures with different inputs, different values of the number 3. But in the modular case, something interesting happens, and what we looked at last time, we saw that the path integral of a 4 manifold depended only on, let's say, W up to, we'll call it borders and rel boundary, so boundary fixed, and that was just it was just an explicit calculation we did. You know, it looks kind of like some weird coincidence, but we, you know, changing manifolds at the bordism is the same as doing some sort of surgeries on them, and we saw that in the modular case, those surgeries had no effect. So and then I claimed, I think, without proof, that there's a sort of similar, almost triviality at all levels of the theory, and then we can define, say, the relation TQFT of TQFT as follows: Z sub K of a K manifold, this is K equals 1, 2, or 3. So I have defined these TQFTs, but for those of you who know, they assign, they're not quite, you know, at first they look like 2 plus 1 dimensional TQFTs, but there are 2 weird things about them compared to all the others that we looked at. One, they only go down to 1 manifold. You can't, there's not a good way to assign an invariant to a 0 manifold. That's one unusual thing about them. And the other is that they require some extra structure. So when I write xk, what I really mean is xk with some extra structure, and which I'll say more about in just a moment. Anyway, so we can just define this to be the z sub, let's call it my 3 plus 1 dimensional theory. Boundary inverse of x. And I should probably throw some boundary conditions in there, but let me not worry about that. So, of course, you know, by boundary inverse of x, I just mean some manifold 1 dimension higher whose boundary is x. And you might say, well, it doesn't matter. And the answer is, well, it matters, but only a little bit. So in dimension, if we take k equals 3, we're saying given a 3 manifold, choose some 4 manifold whose boundary is this, and then evaluate this Crane-Yetter state sum on it. And then the only thing you have to tell me is the bordism class, which is just a signature. You know, it's a sort of a z's worth of information. And then because of the statement we proved here, I showed, you know, we're getting an invariant of a 3 manifold, and that's exactly the Russian T-Triad invariant of a closed 3 manifold. I guess what I should have said earlier is that the input here is the same. It's also, what's the input for constructing this type of TQFT? Well, it's precisely a modular category. In fact, the definition of modular category was sort of designed to be, you know, exactly what you need to make this construction go. So it's not surprising that that's what the input is. Yeah, so another way of looking at it is there's this definition of a modular tensor category, and initially it was, you know, it was sort of reverse engineering this particular construction, and we see that it, from our point of view, the definition consists of 2 parts. There's a sort of braided one category. I should probably throw in fusion or some other adjectives in here, which is just a very natural, you know, that's what you would need to construct a 3 category with the first 2 levels trivial that has the right sorts of dualities. And then there's this modular condition, the fact that this determinant is not equal to 0. And that seems a little funny. and we're saying that this is somehow guaranteeing that this works. I should also mention there's some recent work of Fried and Telemann where they put some of this in a little more general context. I think Constantinos talked about that recently here. Okay, so what's left to do is to make sense of this statement for lower values of k, for k equals 1 or 2. And there's various ways of doing that. The statement would be that, given a two manifold, we want to assign a vector space. So we choose some 3 manifold whose boundary is that 2 manifold, and compute the scheme module based on these things. And that certainly does give a vector space of the correct dimension. In fact, it lines up with something in the restrictive triad construction. But that's not enough. It's not enough to say, okay, we've got a vector space that turns out to be isomorphic. We want it to be functorial somehow. And to get the functoriality right, it turns out you have to remember a little bit about which 3 manifold you chose. And the thing you have to remember is the kernel of the first homology of the inclusion map of 2 manifold and 3 manifold. In some sense, it's a Bordism to use here. And there's similar statements for that. But what I wanted to spend most of the day talking about is sort of...
So that again is just sort of extra structure, the types of extra structure you're meant to be thinking of on the x's for smaller values of k.
That's right. Yeah, so when k is 3, we need an integer, which is secretly the signature. When k equals 2, it's the Lagrangian subspace, which, again, that's not a new idea. That was in my old notes in Taraya's book. They talk about these Lagrangian subspaces and sort of deriving that from this point of view. K equals 1, there's sort of a canonical choice. You can just take a circle bounds a disk. Okay, but I wanted to talk about sort of the fanciest way of seeing this, which is a categorified Merida equivalence. So that's mostly be talking about those in the abstract. Okay, so first let's review Merida equivalence for 1 categories. So what, and as always, when I say category, I'm meaning typically a linear category. So let's say A and B are 2 categories. So roughly, A is Merida equivalent to B. Just means that A is equivalent to B in the 2 category of 1 categories, pi modules, and twiners. So we just have to unpack what it means to be equivalent here, and then we give this the reference. So historically, that's not how Merida equivalence was defined. And if you look at a lot of literature, they give to me it seems like a clunkier definition, but it's not hard to see that it's equivalent to this. And maybe by maybe now in the 21st century, I don't even need to say that. Maybe that there's been enough papers written that say this. Okay, so what does it mean?
Yeah, what's the clunkier thing, just for reference?
It's just, well, I'll remember saying it.
Okay.
Yeah, I'm gonna say more here because I want to set this up because I want to generalize it to higher categories. So, whenever we say the two, anytime you think of in mathematics, you say something is equivalent to something else. Generally, it means the 2 things you're saying are equivalent. You're situating in some kind of category or higher category. And you're saying they're equivalent in some higher sense. So when we're talking about 1 category as being equivalent, we have to situate them in some other category, and that's going to be a 2 category. And there's two cases. The probably the most common case is the 2 category whose objects are 1 categories. Morphisms are functors, and 2 morphisms are natural transformations. And then if said that categories A and B are equivalent in that two category, you would end up with a definition of like natural isomorphism. So but in situations when you're doing TQFT-like math, it makes more sense to go in this different category, same objects, but now we define morphism to be a bimodule. What's the other word people use? Span? I don't know. Yeah, I think people tend to use a different
Correspondence?
word. Yeah, if we're not assuming linear. Okay, so abstractly, here's a couple of objects inside a two category. And to say they're equivalent means I've got one morphism going from A to B, and I have another one morphism going back. And is F equal to G inverse? No, because we're in a two category, and that means that morphisms within some one category, and we should say that those in turn are equivalent in that morphism. So we have sort of a two morphism going from F to G, and another two morphism going back, and those should be equivalent. So it's an equivalence between A and B is sort of this one category of information and some auxiliary two category information. So in this case, what would it be? Well, we would have what's a one morphism from A to B. So now I'm defining a re-equivalence. We have a AB bimodule, M sub AB. So there's A on one side, on the other. So let's just call it F. I should call it M. And then I have another bimodule that goes the other way. And now, let's see.
Maybe you should say what bimodule is.
Okay, so does everyone know what a bimodule of algebras is? Okay, so in particular, it's a so bimodular categories for all objects x and y inside the zero morphisms of our category, the objects of our category. We have a vector space of v sub x, y. And then we have maps to say the morphisms from z to x. So this is in our category, we have a morphism and we can act on this side and we get to zy. And on this side we have an action of morphisms from say y to w. Given such a morphism in this vector space, we get a map from dx w. And then those should satisfy the sort of obvious associativity things. If I act by morphisms twice, I can either act by the morphism and act by the other thing, or I can compose the morphisms inside the category and then act on it.
This will make Kevin cringe, but you can also just take the direct sum of all the Hom spaces and have that's some algebra, and then just have a normal bimodule over those direct sums of Hom spaces.
That's correct, but then when you try to generalize that, the reason I would cringe is that that way of defining it doesn't work so well for higher categories.
Okay, so you can just say it's a
Yeah.
Yes, that works. I mean, and you'd want to take, because we want a left and a right action, you'd say, so another way of saying it's a functor from A cross B opposite into that. And a standard example in the context of TQFTs, if you have some n-manifold then we have a cylinder category associated with the side and a cylinder category associated with the other. This is on, so the state module of this n-manifold would be a bimodule for the categories associated with these n-1 manifolds. That would be sort of, when it talks about extended T-Siegel type axioms, that would be sort of first level down. Okay, so we've got these two bimodules. Now, I said arrows going back and forth between them. I guess what I really should have said is decompose these. We go via M and then via N, and then we have some endomorphism of A, and do we want it to be the identity? No, we just want a map from it to the identity. So that means we have maps. So what's the identity? The identity bimodule from A to itself is A, thought it was a bimodule of itself. In this case here, we would define V sub x, y as to be the morphisms from x to y, and that has actions on the right and left by composing morphisms. And so we want M, A, B, so B, M, B, A, we have some map going this way. See if I can get away with not giving it a B. And I guess, and we also need a map going the other thing. So, and then these are intertwiners of bimodules, so it does make sense now to say that the compositions from either side is equal. So we've got those two arrows. In addition, we have the same thing with the roles of A and B, reversed. But that's not enough. I think often, at least, if you had asked me 5 years ago, I might have told you incorrectly, okay, that's it. But there's one more thing, which is that these arrows have to satisfy a compatibility condition. And diagrammatically, it looks like it's basically saying that this is equal to that. Okay, so what do I mean that's equal to that? Well, this is going to be a string diagram. These bimodules and categories form two categories, so I can draw string diagrams. So I think of A as being over here, and B is over here, and this is just there. And this is, say, MAB, labeling the thing in the middle. So this, and then when I draw it vertically, this is the identity intertwiner from MAB to itself. What do I have over here? Well, the bottom, I just have M going from A to B. And then I compose with one of these arrows. This is the one that goes from B to this tensor product. And now I have M, M. So I'll call this, let's call the arrows 1, 2, 3, 4. So I'm using arrow 3 to go there. And now I can use arrow number 2 go that way, and then, so that composition of intertwiners should be the identity. And similarly, if we reverse the role of A and B, right and left. So I don't know. Looking at one category, that seems like kind of a picky condition. Why would if that wasn't satisfied, where would you ever run into trouble? But I'm not sure how to give any convincing example. But when we see that this sort of condition becomes more interesting in higher dimensions, so that's what I'm talking about. Okay, so how do we generalize all this to higher categories? Well, what we need to do is, if we've got a pair of n categories of the right sort, we need to situate them inside some n+1 category. So I need to say what that n+1 category is. It's going to be some kind of generalizations of this category bimodule intertwiner thing. And then I need to run through this and say explicitly, give explicitly the higher dimensional generalization of this. So that's what I propose to do. And then if there's time left, there might be. Then we'll look at it in the specific case. Yeah, so I guess I didn't, what does this all have to do with the beginning of the discussion? We'll find that so if I consider, this A is not the same as the A down here, it's our skein module type construction, except I want to apply it for this 3 plus 1 dimensional theory to switch the boards. So what's the quote? Skein module of a circle. Well, n is 3, so this is an n minus 2 manifold. So this is some kind of 2 category that we construct from our theory. And I want to say that it's 2 Morita equivalent. 2 Morita equivalent means like the one, yeah, like this, with one category replaced with 2 categories. To the trivial 2 category. So that's what I want to show. And then once I have this, that will allow me to prove the sense in which these lower dimensional variants are sort of trivial. So it's not true that the, if we were to say that the category we started with, which is a point, this one's not really trivial, but if we go up to the circle, it is. Okay, so at this point, we have to, just the fact that we haven't even defined higher categories yet. So, but in a way, but we actually have, well, we sort of did, because we talked about this, the structure of fields on a manifold. So it's a collection of functors, which, given a K manifold gives you some set, and when you glue manifolds together, you have appropriate maps of sets, and they're sort of product maps. And so sitting inside that definition is actually a definition of n category, because we can say, let's restrict our attention to just manifolds which happen to be balls, or maybe the boundaries of balls, and just think of all the different ways we can glue those together. Then for each ball, we just say K ball, we would have some set, which we'll think of as K morphisms indexed by that particular K ball. And the gluing things become like composition maxims in a category, and taking boundaries like taking boundary range, and so on. So, if you want to read more about that, this recent paper Scott and I wrote has all the details. But I guess, but the upshot is we're going to think of an n category as a being sort of picture calculus, stream diagram sort of thing. That's what we've been talking about the past few weeks. Okay, so now I have to find an n plus 1 category whose objects are in categories and whose higher morphisms are something like bimodules or higher dimensional generalization. So how does that go? So we said that in category is a collection of functors from some balls to set. Going to underline mean that these are some kind of categories themselves. So I'll call it a in category bimodule is going to be a similar collection of functors. But now instead of balls, I'm going to call them balls that have sort of a shading and a line down the middle. So here's a 2-dimensional version, the 1-dimensional version with one end shaded. We had a 3-dimensional version. And cut it down the middle. So there's this category. This is 2 colored balls or something, or split balls or marked balls. And we want a functor from that in set, collection of functors. And when we defined the bimodule, I erased it. We had, one of the fundamental things is we have actions from the left and right. And so if we just look at the left or right of one of these pictures, category bimodule, say between n categories A and B, we think of one of these as the A half and the other as the B half, and so then we can glue A pictures on the one side. What do I mean by A picture? Well, by definition, A is an n category, in other words, it's a functor, the ball is a set, and the values of those functors are what I'm going to quote pictures because of actual examples, sort of our pictures. So the gluing, so how many, I guess another way of saying it is, we want to take one of these balls that has the shading and we want to cut it into two pieces. How can we do that? Well, there's three different ways. We could cut here, and then we have a smaller shaded ball and just a ball of one color, say the A color. We could also cut here, and that's the same except it's on the B side. Or we could also split it like this into two thinner bi-shaded balls. And so what these correspond to is a B action, an A action on the other side, and then the whole thing itself, things can be composed. For example, when n equals 2, these balls, amongst other things, form one category because we can stack them this way. If n was equal to 3, they'd be a 2 category because we can, balls like this can be stacked in kind of 2 dimensions. And in addition, they have the actions. So obviously I'm omitting a lot of details, but if to the extent that you're comfortable with this definition of n category, writing down this definition of bimodule is completely routine. So what do we have so far? We're trying to define this n plus 1 category. And at level 0, I have n categories. Level 1, I have n category bimodules. What about level 2? Plus 1. In other words, what's some sort of bimodule between bimodules? Well, given morphisms from, say, I have one bimodule that's this solid line, map it to another bimodule, which I'll call this double dotted line, just a different notation, but two bimodules between the same thing, so both AB category bimodules. Now I can consider an annulus, or thinking of I'm thinking a circle across another ball of the appropriate dimension, and I can consider pictures which locally if you look closely here, you see the first bimodule. Down here, you see the second, and then there's some. You can split up pictures by taking some kind of coordinate that we would associate to these circles. And these circles are themselves some kind of, we can stack them together radially. And they also have sort of an action of gluing more stuff on like that. So there's a maybe it would help if, so if I give an example, one way of make a digression. It's not a typical example, but it should illustrate these things. One example of an in category is pi fundamental n groupoid of a space. So say T. So this means that this is my name for the category. I apply it to some k-ball x, and I just define that to be the set of all maps from x and T. So if we take n equal 1, this is the fundamental group weight of a space. To a point, the objects are points in T, and the morphisms are arcs. And I guess we can say this is mod homotopy. Just the very top. Okay, so what would it, so what's an example of a bimodule? Suppose we have a subspace, W containing T. Then we consider maps of these bimarked balls where that interface in the middle has to land in W. And then what would it mean here? And then, given any W, so we have a for any subspace of T, we get a bimodule. Like this, and those maps can be grouped together in various ways. And so what do I mean by this structure? This would mean maps of this circle across some ball such that this region here maps to one of the subspaces, and this region here maps to the other subspace. So what are we going to call these things? They're not exactly bimodules. So S1 module.
Wait, what are the? So you want like balls with a slice through them, such that the slice maps to W.
Yeah. So given a ball, yes. What I want is
My question is, what you're considering maps of something into a target space T.
Mhm.
And what is that set of somethings?
it's initially it was a ball with with a sort of thing dividing down the middle, and the example I was giving is where this interface in the middle has to map to some subspace.
Right, so right now are you being precise about
What these things are?
what those things are?
Okay, so I can draw a standard example. I just take the standard ball and consider the standard
Yeah.
thing right there, and it's anything homomorphic to that.
Okay.
So it doesn't have to be canonically isomorphic to this, but it's the category of.
But then that picture with the O is not the same.
Right. So so to define an S1 module, I want things. I can construct this a standard one of these. I take my standard circle, cross with the standard ball, divide it into two pieces. Now I consider anything that's homomorphic to that category of Mark manifolds,
Okay.
and I've got a functor from that. The thing, but what I. So that's.
The functors from that.
Two.
What are the morphisms in that
Homomorphisms.
category?
Yeah, so the functors here, this is functors of just plain one category. So category of balls plus homomorphisms. Same thing here.
So far there's no blue and
Yeah, no, this is just sort of the some of it. Because of time constraints, I'm just trying to give the high points of the definition. All of these things should glue together in a reasonable way. Meaning, in particular, suppose I had a second ring picture that I might draw on here,
Yeah.
or if I glue them together, so And there's some other axioms about sort of isotopy invariance when we hit the top dimension, and being able to take products and things like that.
Are these S1 modules coming from some class of examples you have in mind, or is there a reason why we don't just take all manifolds with these slices, or I mean, why are we choosing these specific ones?
Well, you mean just like an arbitrary manifold that's divided into two pieces?
Sure.
Yeah, no, that would be, so the difference there is, at the beginning of the course we talked about fields or functors from any manifold in the set. And then we see that in some sense that's determined by just its values on the simplest possible manifolds.
Does they claim that these are the two that you need, or these rings and these?
Yeah, so in some sense these are in terms of manifolds that are marked. So I guess in language it might be, another language is, in physics language this is some kind of defect between like two field theories. And then this picture would, of course, we've got one kind of defect, and then we have another kind of defect, and then there's some defect between the defects in here. So if you just think of like a neighborhood around that second order defect, it looks like this. So these are the sort of obvious, simplest pictures that exhibit sort of phenomena. But we could, if we wanted to skip that step, just define.
Sorry, where's that second order defect in the ring picture? Is that at the top? Or
It's whatever fills in the hole.
whatever fills in. Okay. Okay.
Like in particular, the Kevin is saying that associated to that annulus is some one category, and the
Yeah, but I actually should have, I think I misspoke a little bit. Let me, so I'm going to revise the remarks I made about thinking of S1 picture. Given two bimodules, I can construct this will be an n category. If we start these things, n minus one category. If it's a bimodule between n categories, after we do this construction, we've sort of used up one dimension by making a circle, but we still have n different directions that we can move things together. So there is this n category, but what an S1 module is a representation of this n category. In other words, it's some, for every picture like this, we have some vector space or categorical version of it, and when we stack these things, we act. And so this representation is somehow the thing that labels a point. And given a picture like this, you can move stuff on the outside, and that's the sense of it.
So this is really kind of a germ of a point or something that we're thinking about here,
Yeah.
and then you want to...
Yeah, maybe the link of think of this as the boundary of a small neighborhood of one of these second order defects. Similarly, instead of a bimodule, we could have called this an S0 module, because S0 is just 2 points. And you can continue in this way until eventually, I said this thing is an n minus one category. Well, eventually, when we get far enough down this list, it's just going to be a one category. And then what's the map between one category things? That's just an interpointer. The step above it was just defined to be a representation of the category model. So this is our higher dimensional generalization of this familiar category of two categories, one categories of bimodules and interpointers. So one thing you should do is think about the n equals 1 case and see that it does amount to the same thing.
So is there a precise statement along the lines of, if I take marked manifolds and look at some sort of bimodule theory, that it's determined by this type of bimodule, or what's the right word? S-module theory?
Yeah, sphere module is what we're kind of thinking of a better name. So this is the what we define as the n plus 1 category of n category sphere modules.
I guess should this picture be obvious that I just start cutting and cutting and cutting until I only have these sorts of pictures left, or?
You're asking in what sense is this definition inevitable or optimal or something?
I'm just curious. I mean, field theories give a lot of different ways that things could act, and this is one interpretation. It seems like a very natural one, but I'm just wondering what else there could have been.
Yeah, I mean, the other things I'm aware of in the literature are, in which I think is kind of the wrong way to go, is what people sometimes do. Let's just take n equal 2. So we have this categorified bimodule, which are sometimes referred to as bimodule categories. So instead of a family of vector spaces that has actions on either side, we have a family of categories with action on either side. And then you can consider a functor between bimodule categories. That, for equivalence of 2 categories, that's probably more common definition. But to me, it feels kind of wrong because, there's a very early fork in the road. Are you between one category? So we have bimodules or do we have functors? And once we've decided to start using bimodules, I think we should continue to use bimodule type ideas and not sort of mix these things together and talk about functors. You can think of a functor as being a special case. Given a functor, you can construct a bimodule, but not vice versa. It's not easily vice versa. I guess.
Yeah, I mean, so I think that the end of my conversations with Shomapris about this was that.
There's some equivalent. Yeah, but
that as long
higher.
Yeah, I have no idea about higher, but
Okay, so anyway, so that's one thing one might do, and to me it feels a little bit.
Yeah, these natural transformations in certain cases are exactly bimodules. I mean, if you write things
Yeah.
in
But
appropriate setting, but I guess you want to be absolutely sure that they are the right kinds of bimodules.
And I think for this sort of form, I think if you look at just papers written by physicists about defects and things like that, this sort of like caboose comes to mind. And this sort of language fits very naturally with what they're saying. It's pretty similar. So to me, this seems like the obvious thing to do, and I can't think of anything else that seems reasonable or natural.
Is there some kind of cutting or gluing theorem about this? Again, with this sort of, if I started with manifolds that were colored, basically just defects.
Yeah,
and some locality assumption, then I would get this.
I mean, one. Let me try to answer that. Okay, so we're trying to generalize this definition of Morita equivalence, and so we now have our target category, and it should be roughly clear how to proceed. We say the 2 n categories are n Morita equivalent if they're equivalent within this n plus 1 category of serial modules, blah blah blah, which means that we've got one morphisms going back and forth between them, i.e. a pair of category S0 modules, and then between the compositions there we have higher morphisms, so on until we get to the top layer, and then we just insist that 2 things be equal. Some composition is equal to the other. So that sounds like we'll have to, the data for the equivalence is going to be something at each level, 0 through n or n plus 1. But actually it's less than that. Because implicit in everything I've been saying is a certain amount of duality. And these balls that I consider, they're not balls with some kind of framing or vector field that tells you which way is up vertical, which way is horizontal. We're allowed to twist them around when we want to. So it turns out that the only data we need is, well, we need 2 pieces of data. We need that at level 1, and we're going to need something else at level n plus 1. And then we're going to have some conditions analogous to these sort of zigzag things that I'm going to write down. So all the stuff in the middle comes for free. So that's one, and the reason we get all this stuff for free is that we're in a context where we're assuming that our categories have some sort of dualities. Higher dimensional version of total. Okay, so let's spell that out explicitly.
With less duality, is it clear what happens? Can you kind of piece it together, or does it get too complicated?
I haven't worked out, so the question is, can you even define a category of less duality in using these sorts of ideas? And my feeling is yes, but the details are proving a little bit tricky. the first thing is say, oh yeah, just use framed balls instead of regular balls, but that doesn't quite work because of having to get identity morphisms to work out correctly. But I think the intuition's right, and so once those technical details are overcome, then something like this would work for categories without duality, and there would be some kind of structure in their pictures that are this kind of distinguishing the different directions things can be stacked, and maybe it doesn't allow you to turn things upside down. But again, details not intuition. Okay, so maybe I'll just take n equals 2, just to be concrete, but everything I'm saying generalizes easily to the higher two in the case. So I've got two categories, A and B, and then two Morita equivalents consists of the following. We have AB bimodule, once categorified bimodule. So AB. And because of the duality, we can, it allows us to turn them to go, if we have some way of drawing pictures where we have A on one side and B on the other, we can certainly flip that around to do the dual. So I don't have to, here I had separate M's and N's. But in the duality case, that's the way I have to specify. So we've got some bimodule. Given that bimodule, what can we do? Actually, maybe I'll just draw the pictures first and then explain what they mean. Okay, so this n plus one dimensional data for my two marine equivalents is going to be these 6 arrows. Okay, so what are these arrows going between? What do these pictures mean? Well, first let's look at the boundary of the pictures. On the boundary, one can imagine taking a color neighborhood, and so there's so here would be a circle that's entirely covered by B. Remember, B, blank color is B, and my shaded color is A. Here, if we look at the boundary circle, it's something that has an alternating, has two A regions and two B regions, and they're separated by, these lines should always be thought of as M. Remember, M is some kind of picture calculus type thing that allows us to make sense of pictures that have sort of A stuff on one side and B on the other. So here I was saying that once given a couple of bimodules, I can form this. Assuming that n equals 2, I can form this one category of annuli and stack like this. I can do the same thing with annuli, which go back and forth twice. Implement that. And then, of course, I should also mention that given a 2 category, I can form a 1 category, which is just those sorts of 2 category pictures drawn on an annulus. You can still stack them in one direction. It's sort of like it's called the Trinfeld center double. And actually tomorrow we'll talk more about that.
That's radial stacking.
Yeah, radial stacking. Okay, so we've got, so here's 3 different categories that we can form. This one we can form just from A. We've also got this similar ring form just by B. And then given a bimodule M, we can form many more things. But in particular, we can do this version here that has 4 copies of M. So here's 3 different 1 categories. I claim that each of these disk pictures gives us each row here gives us a pair of representations of one of these categories. So how does that work? Let's take the middle one. In the disk, I have for any sort of fixed stuff on the boundary, I have all pictures modulo relations that fit like this, and that's going to be some kind of vector space. To be concrete, in the example I gave, where maybe A is equal to B is just equal to maps into some target space T, and M means that you have to restrict to some subspace. This would be maps of this loop into T such that these 4 points it lies in the subspace. To give more, we might consider our target space T to be divided into 2 regions. So this is not exactly the same as those pictures, and we can T1 and T2, and then we could say that A is isolated T1, where again I mean the groupoid version of pi n. B is T2, and then M is maps of balls which map one side here, one side there, and indeed this does have an action. Yep. Okay, so we've got this this one category of circles mapping in this way, and I wanted to find 2 different representations of it. And these 2 different ways of filling this give us 2 different ways of doing it. And so these arrows then are intertwiners between these modules. So endless one-dimensional data is 6 different intertwiners between various in-category modules. Okay, and now what are the identities these things need to satisfy? Analogous to this identity. This is that. Well, you can think of this as having to do with sort of a cancellation of a 0 and a 1 handle and some kind of Morse. You can think of this as a graph of a Morse function on this arc. And so we just do the same things in higher dimensions. So given so I draw this picture. What is it? Well, it's going to be a module. So first we look at the boundary. You see a circle like that first one I drew up there. And so this filling in with this disk gives us a module for that category. Now consider this picture. Okay, the boundary is the same, so this gives us another module for that category. And actually we have, from the data over there, a module map between these things, because we can look at just this region. And because things move together nicely, we can take this map that takes just a sort of B region into something that's got this A stuff in the middle. That gives us a map there. Now we can look at just this ball. Take, so what do? We joined 2 black things together, so it would be, again, the arrow going this direction. That gives us a module map there. And on the other hand, these 2 pictures are isotopic to each other, so there's sort of an obvious map that goes directly there. And so one of our conditions is that these, and so all of these things are intertwiners of modules, so it makes, we think in terms of category level, we're down to category level 0, so we're going to say that they have to be equal to each other.
So just to rewind a little bit, I'm not
So you mean
Are
like
there
defining.
maps of sets, or are there like natural transformations of the vectors?
Oh, they're maps of vectors. So they're intertwiners between representations of one category. So what's a representation of one category? It's a collection of vector spaces. So an intertwiner is a collection of linear maps.
So this is just a natural transformation between the two.
If we think the representation is functor, then yeah, it would be a natural transformation. So we want this condition to be true. And if we think of this as some kind of Morse function on a two-manifold, we could draw a three-dimensional version of this that would look like this, but one dimension higher. Alternatively, I could take that picture and draw it as a series of one-dimensional pictures. Let me do it here. We'll start out with A and B, so I've got this shaded region, and then I map. Add some other shaded stuff there, and then I get rid of that. So this is sort of the time slices of that picture. And what I've drawn here is the time slices of some three-dimensional. Okay, so how many pictures can we draw like this? Well, this has to do with cancellations of more singularities on a two-manifold. So we've got 0, 1 cancellation and 1, 2 cancellation. But those, and in addition, the two sides could be covered by A or B. So it turns out that up to symmetries, there's 4 different conditions we have to check instead. So that's our definition of a 2 Morita equivalence. For an n Morita equivalence, it would be very analogous. We'd just be drawing higher dimensional pictures here. We'd have to think of all the ways that Morse functions on n manifolds could cancel. Okay. So what are some examples of higher Morita equivalences? One is the thing I mentioned at the beginning. If C is a modular, it's a category, then call it A sub C of S1 is some kind of 2 category, and that's equivalent. Trivial thing. Another example is given. This is for the. Do we have any sub? Okay. For the subfactor people, suppose I have a pair of principal graphs. Let's take the hover up. So this is just the data of some kind of picture calculus where we've got black and white shadings. And in particular, we can look at the even vertices. If we look at the even vertices of this, we get one 2 category. And look at the even vertices here. We get a different thing, and we notice here we've got 6 dots, here we've got 4 dots. So with these two categories, one of them has 6 simple objects, the other has 4. But they're still pivotal 2 categories, and it turns out that I don't know what to call call it even sub black is 2 read equivalent to the even category for black. So this is a sort of a non-trivial thing because as one categories are definitely not, or, if we think of them just as one categories, the read equivalence is determined by the number of simple objects. Not the same as, or since they are. Third example, if G is equal to a finite group. Then, on the one hand, we have the representations of G, which is a symmetric tensor category. And symmetric tensor categories can be thought of as in categories for any n. You just draw these ribbon pictures, in manifold and symmetry. As it works out. And on the other hand, so let's say A is equal to that, and B is equal to the fundamental n-groupoid of the classifying space of G. And these are also in-read equivalent. One thing I forgot to say, I left out something important, which is the sort of basic theorem. Save it on this board. So, assume that A is in read equivalent to B, where A and B are in categories, of course. Then we can we have the TQFT be built out of A, the TQFT be built out of B. And I'm going to regret I'm going to change this to X and Y because the letter A is already taken from the screen module. Then the TQFT construction assigns, say based on X, assigns to any X is taken K manifold some n minus K category. And similarly, we can take the TQFT construction based on Y, apply the same thing, and get another n minus K category, and these two things are n minus K. So in particular, if we think of, say, the scheme modules, that means that they, read equivalence for vector spaces just means the vector spaces are isomorphic. So it means that the Hilbert spaces will be the same based on the two TQFTs. So that means if you, here implies some things that might not have been immediately obvious. We take some manifold, we consider all the ribbon pictures with these representation D's drawn in it, and get some vector space, or we can consider maps into the classifying space and homotopic classes of those. Those will turn out to be the same. It's sort of related to the fact that the number of representations of a finite group is equal to the number of conjugates and classes. That's the n equal 1. If we did this to take n equals 1, apply this to a circle, then we're just looking at equivalence classes, basically the path components of loops of BG. That's the number of conjugacy classes, 3 loops of BG, the number of representations. This is saying that if we build some kind of Tarai-Viro sort of vector space for a surface using this kind of different looking data. Spaces.
Kind of a bundle version of this too. If, again, with n equals 1, it's the G bundles on the circle, and I can read off holonomy, and that's.
Yeah, that's sort of.
And so for n, this is kind of like n bundles or something, or what? So some geometric here.
Any dimensional map.
What?
G bundles over any dimensional map.
Well, but pi n is going to look at for n spheres.
Well, yeah, well, for any manifold, we're going to have the homotopy classes of that manifold in VG, which, you're right, it's higher homotopy, but it's way more natural to think of it as the isomorphism classes of G bubbles. And so, yeah, so the one way of these things, one can imagine some kind of pairing between them, because given a bunch of these Rev G pictures and given a finite G bundle, you can sort of take Holno and more general, say sometimes have vertices. It's like, is this a Wilson loop sort of idea? So it's not, maybe not so terribly surprising. So what I was going to do, I was going to now have the audience, so I actually write down an explicit immediate equivalence and check everything for one of these examples. And there probably isn't time, but I could say what in 5 minutes. So which one? So there's one that was relevant to this actually good triad stuff. There's this finite group thing here. This one I'm actually, I'm not going to offer this one because I haven't talked about this one. Anybody care which one we look at? Neither. Just call it
Sound
today.
good to me.
Excuse me?
They both sound good to me. The finite group one might be a little bit easier to think about.
Yeah, I mean, this one's nice if you're already familiar with this sort of ring calculus. This involves a lot of handle sliding and manipulation of ribbon diagrams, which is easy if you've seen it before, but you all understand. So maybe this is better. Okay, so
I look for finite.
okay,
But I also am curious about if you have anything to say about general Lie group.
I think that's a very interesting question, because certainly for more general Lie groups, we have these sorts of maybe quantum deformed things. We have these ribbon type pictures. That's the same modular tensor category sort of thing that goes into here. And we can take traces, so that part makes sense. Now, what would you replace this with? You can think of flat bundles and then so yeah, I wish I knew the answer to that, and every now and then I think about it, but I don't know exactly what to say. Okay, so what's the bimodule here? Given a ball, draw a line down the middle. One side is going to be the ref G side. This one. The other side is just the G. G. And I have to, for some fixed boundary data, I have to give you a set. In the top dimension, I have to give you a vector space. So let me consider the top dimension. So we can consider maps from this side into G, BG, excuse me, which extend whatever boundary condition we're given. And here, the boundary has some labels by G representations, and you can consider some other network of G representations, and then they terminate, allowed to terminate on here. And every place that they terminate, so a representation of G, I'm going to identify that with flat vector bundles on VG. So at these, along the boundary here, when these two things come together, I have, on the one hand, I have a point in VG from this map, VG. On the other hand, I have a flat vector bundle, so I can pick up the fiber of that vector bundle. And so I've got sort of a vector space associated to each of those, and I can take, so call that row here, I've got the E sub rho is my flat bundle, and then I have a point that relates here, and so there's, I label it by some element in the fiber. And now, so that's sort of to each such picture, told you a vector space, but what I need is a vector space that depends only on the boundary condition. So now I want to mod out my relations, and the relations are, well, this map, I'm allowed to take this map G and homotop it. And of course, the homotop is fixed on this boundary, but it's free in here. So in particular, we can kind of make the map, we can sort of contract the map from this ball to this ball. As the map moves, we can use the fact that these are flat bundles to sort of parallel translate these vectors around. So that, and then the other thing we could do is we could imagine having this shaded part kind of engulf something here. And so in particular, let's consider one of these vertices in a Rep G picture. We have some representation rho here. Sigma 1 and sigma 2, those are some G representations. And then the label here is some intertwiner of G representations from rho. So this is labeled by F. This is F coming from rho to sigma 1, so sigma 2. So there's a corresponding map of the flat G bundles, and as our this interface crosses from one side to the other, we just use this map of boundary data. So, so we have all such pictures modulo those relations. Now the quicker way to say it is if we look only, if we, let's forget about the stuff in the middle, let's look only at the boundary. Then what I'm left with,
Sorry, you're describing the set that you're assigning to
the vector space.
the vector space.
Vectors at the top dimension. In lower dimensions, I would just consider such pictures, which are pretty true. But I've got a, and maybe I should take n equals 2 for concreteness, and that's sure we run here. Another way of saying it is, at least up to isomorphism, I've got some points on the outside here labeled by representations, and up to isomorphism, I'm just taking the underlying vector spaces of these representations and I'm tensoring them together. But the problem with that is that it's automorphisms, and so I need to not just tell you what it is up to isomorphism. I need to give a very concrete picture because this is convenient. But all this complicated stuff I've been describing, modulo moves like this, just boils down to that. Okay, so now, and is this a bimodule? Well, yes, because we can extend the G map. If we do on a map here, that's just a map into BG, we can extend. And if we have a map here, which is some stream picture for our G pictures, we can do on. That all works out fine. It's 12, I guess I'll go on to it needs to go, I understand. Okay, so what is it? So how are we going to verify? Well, I guess the next thing we need are intertwiners like this. In fact, we can take, these pictures are conveniently drawn in 2 dimensions, so they're ready to be interpreted here. But I think actually, I'm going to replace this with an equivalent category. So, given a map in the BG of some manifolds, we can. So here's my manifold, and it's mapping in the BG, and I can choose some cell decomposition, and then I can try to on each of these cells, I can kind of crush the map down to the base point here. And then on each, think of the dual thing. So each point is going to go to the base point, and then each transverse one cell is going to pick out some element in the one skeleton of BG, which is just G. So we label these things by G. Or in other words, we label these codimension 1 things by G. And then when 3 of them come together, this is labeled by G, and this is labeled by H, and this is labeled by GH. So this category maps in the BG turns out to be equivalent, not just an read equivalent, but in the stronger sense equivalent to these, I'll call them G pictures on a manifold. And I just mean a bunch of codimension 1 faces labeled by G, And then when they come together, there's this sort of associativity condition.
This is just the simplicial model for VG, the simplicial
Yeah.
model.
So it's going to be, for concrete calculations, it's going to be more convenient to have that sort of picture. So what would this become then? On this side, I would have these codimension. Turns out n equals 2, codimension 1 is the same as dimension 1, but for the higher dimension generalization, we should think of these sort of hypersurfaces labeled by elements of G. And now, the point it's here, I just want to assign some vector in the underlying vector space of rho, and then if it passes G, I want to act by G. So if I've got, so pictorially, that means rho G X in the vector space for rho, that's equivalent to the picture right. I move them past each other, and now I would assign Gx in the vector space of rho. So that's the solution. Okay. Should I keep going? Or? I mean, so let me quickly sketch how it goes to the end, and I'm happy to go into details, but I know I've been talking a long time. Well, I mean, the details is we just write down explicitly what all these modules are and find intertwiners, and it ends up, there's this fact that the regular representation of a group is isomorphic to a bunch of sort of a sum over conjugacy classes. Some comes in. So it looks like you're not done. I'll continue. Okay, so I've got to write down 6 intertwiners. So before I talk about intertwiners, I have to identify what the category is. So we'll say that the shaded side is rep G. Outside is G. So here I have basically loops in G. On the outside, I've got a bunch of transversely labeled category whose objects are points on a circle with these transverse G labels, and morphisms are pictures like this, but in an annulus. And up to equivalence, we can just assume that we've got a single thing here labeled by G. And again, up to the equivalence of moving this around, we can assume that we can sort of clear everything else out there. So we think of the single label G, if you like, it's just this is describing a map of the circle in the region. And here I have a bunch of representation pictures, but again, using these sorts of relations, I can squeeze it down until it looks just like this. And
what did you just draw?
oh, let's see. So let's see. Well, close up. I have some arbitrary picture of representations of G and their intertwiners, like this. But then I'm allowed to manipulate it up to isotopy, so I can. So in some sense, I can make the whole thing disappear. But yeah, okay, let's take that route. So I can. One thing I'm allowed to do is push this interface past things. So that means the whole thing is spanned by the empty picture. Okay, so what I've drawn here, the only boundary conditions I have to consider are a single element of G And then any picture looks like this. Of isomorphism.
It
But
just has to do with the fact that the ball is contractible, so that
yeah,
the G bundle is trivial. Is that something
yeah, it's kind of dual to that because I guess it was the G bundle is somehow out here on the annulus. I mean, and the annulus is not contractible. That's why I have to there.
or like the inner annulus is contractible, or sorry, the inner ball is contractible, the outer ball is contractible. There's a difference. There's a difference between the two trivializations.
No, I don't think that's it. I think it's better. I think, because these ribbon pictures tend to only see pi 1, it's like saying that the relative pi 1 of disk modulo boundary is 0. That any sort of one-dimensional thing can be pushed out to the boundary. So I'm using that. So these pictures span this module for this category here, but are they linearly independent? In particular, are they non-zero? And I claim that if G is not equal to 1, this picture is actually 0 because this picture is equivalent to one where I take some representation rho here, and I have some elements, this is going to be some vector in rho tensor rho, and it's essentially the identity. And then I can run this around the edge and pass G, get back to itself dot. So I've got somehow the identity going to E sub rho tensor E sub rho star, and then I have G tensor 1 going to B rho tensor E sub rho star. That is because I passed the ribbon and then I'm using this relation that I wrote down here. And then I have a map from here back to 1. And so the question is this map the identity or is it something else? Well, G, if I've done things correctly and G is equal to 1, then it is the identity. So the picture we have the identity there is fine. Anything else I can find some representation that detects the variable G. So G is not 1, this picture is 0. Okay, so now I just describe this representation of this sort of category associated with the annulus here. What about here? Well, here we just have maps into VG, and this is the thing given by disk. So when does the loop described by G, when does it bound to disk? Well, exactly when G is equal to 1. So these modules are isomorphic, and there's sort of one-dimensional, so there's obvious maps going back and forth. Okay, so we can go to these two pieces. So this one is more interesting. So first, this outer category, if I draw it out, so here's an annulus that's been wrapped around, so I identify the two ends. I've got two regions where I have shaded two rep G regions and two G regions. But up to equivalence, we're sort of allowed, so we have maps from here going into VG, but this whole thing is kind of contractible, so we can what I want to say is that any object is equivalent to 1 where I just have some single representation here and here and no sort of a trivial map or no elements of G there. So I have to consider everything's real. I mean, given that boundary on the data, I have to give you a vector space. Okay, so I can manipulate, again, I'm allowed to, got these fixed things on the boundary, but I can, again, just sort of push them to the outside. So any picture is going to be spanned by one like this, and so the vector space is just going to be, it's an V sub rho times this and V sub rho prime. So again, to review what I've done, and I've skipped some steps, I've looked at this category. I make some claim that up to isomorphism, any objects in this sort of annular category look like this. I take one of my small list of objects, I put it here and say, what does this vector space look like? And I do some more simplifications, and it's just this. So surprising. That's the vector space over here. Well, I can take the same boundary data, and again, these things just run to the edge, and I get an isomorphic vector space. Yeah, so this one's looking, again, kind of obvious. So I think it is. I think that this would be the interesting case. And so the map between, so given this data, I can, I just send this picture to that picture, where because sort of nothing's going along in this region, so I can change it. Doesn't matter. Okay. Finally, we get to this case, which better turn out to be non-trivial. Otherwise, I've made a mistake, because at some point I have to prove something. So no, I think I said something wrong, because here, if we think of the boundary data, we've got maps to BG on this arc and this arc, and I said I could assume that they go to the base point. So this is trivial, but the relative pi 1 for, we can still have, we're thinking of the maps to BG case. So basically I have this sort of rectangle, and I'm mapping the ends to the base point, but the middle can wrap around some non-trivial elements. So in going to this sort of dual picture of maps into BG, it means I can have a third-dimensional face here by some arbitrary thing in G. So
Actually, you have to run out for just a few minutes, but if everyone leaves the room, it's more time I can do.
okay, I'll wait for it. Yeah, sorry about actually, one, I thought, I've been through this recently, but I don't have the notes with me. On the other hand, I thought I was unlikely to get this far anyway, so surprise me with your patience. So So if we look at pictures like this, where we've got some vector space V sub rho here, V sub rho prime there, and we're looking at elements of the tensor product of these vector spaces, modulo G acting, so that seems to suggest the invariant part. But G. No, I think what would be better is if I finish this off at the beginning of next time, because I think the answer is short once you think of it.